So let me start this chapter 17, which is about the chemical kinetics. It came to my mind, so I want to write this one more time and talk to you before actually I want to write some section. This is what is called ammonia synthesis. This is a Haber process, where actually our modernization of agricultural life and modern chemical life is really relying on the chemical way to produce something that is important, chemical ammonia. And I think that in our previous chapter 6, we talked about how to calculate K value and what's the temperature dependence. And this is an exothermic reaction. This is an exothermic reaction. So therefore, by increasing the temperature, your K values based on the Van 't Hoff equation, it comes down. Okay? You remember the exothermic reaction, you heat it up, equilibrium shift to the reactant so that you favor the reactant over the products. So if you're just looking at this is a better condition over higher temperature. Okay? But if you look at the actual plant is, I think this is something like that, right? Okay, something, I don't know, 200. I'm just give a figurative number. So it's a heated reactor, and the K value is much favor the reactant, right? So reactant, you see the figures, 10-to-1 ratio, right? So they favor the reactant, but the actual plant is run at that temperature. And why is that? It's because if the chapter 6 is about equilibrium, and nothing about how fast can I obtain the reactant. So it's about the kinetics, the time dependence of concentration change has not been discussed. This perspective is essentially if you get sufficiently large enough time and it reaches a certain state that things doesn't change, and rest in peace, and that's what the equilibrium is. All right, this chapter is, we are going to talk about not big K, is a small k. It's called the reaction rate constant, and this reaction rate constant is essentially determine how fast it can go. And one of the big concept is, this is your reactant, this is your product, and what they call reaction coordinate as a change from the reactant from the product. And this is, let's say this is an energy or potential. They call it energy. And this is a diagram is quite widely used. Okay? This kind of diagram. And what that means is, this is your reactant, this is your product. The energy differences is you are going down. This much of the energy will be liberated. That's a delta H enthalpy, which in the form of negative. That's an exothermic reaction. So this energy difference between these two is what we talked about, and probably we can convert that into the delta G and do the whole thing. But now we are talking about this. You have to overcome this barrier. This is what we call activation energy. And the higher the activation energy, and if this person has to climb the Mountain Everest to be in the other side of the mountain, which is, I guess, Italy, there's actual real thing happened, right? The troops, Hannibal troops, climb the Mount Everest or something. This is Mount Elps. It's not Everest. Anyway, the big mountain that they climb it and then came down. And then is coming down to the other one. So that's why they do not want to make a change, although this will be a much nicer state to be. And this is an activation energy that you have to pay. And if somebody has developed kind of to lower the activation energy, and then they will not change any chemical thermodynamic difference. So they will not change any K, but because you can reduce the activation energy, and so that now you don't have to use this high temperature to overcome that activation energy. You can reduce the temperature and you can favor much more higher product too. So it is a balance between thermodynamics, kinetics, and where there's all the chemical engineers and other the chemical industry people, these all actually make a living out of this. And this is the one that controlling this is what we call the catalyst. Okay. So for example, the hydrogen do not react with nitrogen right away. After hydrogen goes to the surfaces, they kind of lose their bond, and at the activated surface of catalyst, and this atomic hydrogen is easily react with the nitrogen. So they try to really change the environment where the reaction is happening. But now you see it's all about kinetics. Okay? So this kinetics has we have to really do the 17A, which is rate of reaction. And they use this, it's like a velocity, it's like a v, it's a v. And this v is mu j dt. Okay, so this is one that we're going to use a lot. And then the 17b, which is the most probably, when people say kinetics in the introduction level, this is a one, and this is what they call integrated. And this is essentially A goes to P, and we can talk about first order, second order. This is all we are going to deal with it, and this is going to be very important for you to develop the concept about reaction rate and dealing with an actual example. And then now the concept about this. This is a new term that people are using in the kinetics, and time half, right? What do you want to call that? It's called half-life. Okay? This is a time for your initial concentration of A. We call A naught. Eventually, they're gonna decay down to the product, so your reactant constant change to half of the original concentration. How long does it take? It takes half-life. And people measure that and tabulate this half-life. Whether half-life depends on the initial concentration or not, they can give us a clue about what kind of order do you have. Once you know this, understand the rate and the essentially rate law, if you know this, you have a predictive knowledge about where to stop the reaction and to retrieve your products and so on. And I'm going to skip the 17C, jump on to 17B. Arrhenius. Have you heard about Arrhenius equation anywhere along here? Now you hear it again. Okay? So this Arrhenius equation is actually specifically about rate law dependence on temperature. Do you see that if I do a little cheating, equilibrium constant as a function of temperature. We know this, right? You know what you call this? This is Van 't Hoff, right? That's the Van 't Hoff equation that natural log K depends on 1 over temperature. You remember that? Right? We just did a quiz on today, and this will be a quiz for next class. And that's, well, maybe not. I don't know, depending on the progress. But this is a one that's essentially following the same thing, and this is our Arrhenius equation. And this Arrhenius equation works really well for something that is sort of the thermally activated process, and it is widely used, and it works really well. It just, they don't have any, the equation, they justify with a fundamental insight, but it does not actually have any fundamental insight at all. Okay, just the way that they just say, oh, it works, so let's just use it and that kind of thing. But later, somebody like Boltzmann actually figured that out. Yeah, it's a rate law is on 1 over density is activation energy, and that kind of idea came up. But Arrhenius itself he's the one that when it first came out, he's actually borrowing the Van 't Hoff equation idea and taking a side tour. So I told you that the one who won the first Nobel Prize is Van 't Hoff. He won the third Nobel Prize. Okay, I guess they're kind of related. And then the last one is very involved, and I would like to sample some section. It's called what do you call it? The reaction mechanism. Okay. So this is called the reaction mechanism. And this is quite complicated when you start to put things into actually something that is realistically meaningful. And for the last one, I just give a sample on this. If I have put a methane in my reactor, okay, and then put a lot of chlorine there, okay, chlorine gas for the chlorination, you will make CH3Cl, CH2Cl2, CHCl3, CCl. Right? What used to be a methane, the smelly little like cheap gas that we just want to boil, or we could burn it as a methane gas, just has no little commercial value. It has a commercial value. Do you know what do we call this? Does anyone have looked at that in the chemistry lab? There's a methylene chloride, dichloromethane. You know what we call this? Trichloromethane. Do you call that? If you say trichloromethane, you are not chemist. Okay. What do we call this? Have you heard about chloroform? This is a chloroform. This is the most common solvent that we can cheaply make from the cheap source with the chlorine. And this is a carbon tetrachloride. Yeah, it's an interesting solvent. It is probably you remember your general chemistry day, CCl4 is in polar or non-polar molecule? Non-polar with a polar bonding, right? This is a tricky one, right? This is a polar molecule with polar bonding. And usually the polar molecule has a much more better solubility as an organic solvent. So this has a better commercial value to me. Okay? And this. But if you guys think about this is a methane, just put it into a reactor and do the chlorination to death, right? Just continue to do that. And at some point that this thing will show up and come out. And the second one, methylene chloride will happening and will go away. Chloroform will happening and go away eventually. If you just let it go for a million years, nobody is waiting for a million years, and then you'll have everything converted to CCl4. Right? But you want to stop in the middle to whether you want to sample this one out or that out, and this is your job to figure the kinetics and then stop the reactor and then just retrieve your products. Certainly your product contains those mixtures of everything, so therefore you need to do the distillation to purify that you learn in the chapter 5C about the distillation and process, but this is all related to how we actually obtain some pure chemicals, and then there are some series of reactions, and this all has something to do with the kinetics. So that's why the last two classes is going to cover the kinetics on this portion.